Okay, so we're starting the section on derivatives. Let's begin. So to understand the concept of derivatives or why we need derivatives, we actually first need to understand the problem that derivatives help us to solve. Okay, so let's start exploring that problem first. Now, I'm assuming you already know how to calculate the gradient of a straight line. I'm assuming everyone is already familiar with that. Just in case you're a bit rusty, let's go through a quick example and I'll show you how you calculate the gradient of a straight line. So take a look at example one. I doubt you need me to explain it for you, but it says calculate the gradient of the following straight line and what is the gradient at any x value on the straight line. Okay, so take a minute, complete it, and then we'll go through it. All right, let's go for the answer. So you calculate the gradient of a straight line using the following formula. We commonly denote the gradient to be m. It's just convention. M, we know gradient of a straight line. It comes from the equation y is equal to mx plus c, but m is equal to. Now, the gradient of a straight line is the change in y over the change in x. That's what gradient means. Change in the dependent variable over change in the independent variable. Okay, so how do we get change in y over change in x? So change in y is we can take y2 minus y1 over x2 minus x1, where x1 and y1, though that is one coordinate, this looks like an x, it's a y. Okay, x1 and y1 is a single coordinate on this curve, it's not curved straight line, and x2 and y2 is another coordinate, or different coordinate rather, on the same straight line, right? So this is really easy. So let's take y2 and let's take x2 and y2 to be this point on top, and x1 and y1 to be that point on the bottom. You're going to have minus 1 minus 11. Be careful about your brackets. Those are very important. If you don't have those brackets, you may just miss one of the minus signs and have minus 1 minus 11. Okay, just take note of that. Over, and then we're going to have 3 minus 2. Okay, so it's going to be minus 1 plus 11. That's going to be 10 over 5, and that's equal to 2. Right, so the gradient of this straight line here is equal to 2. What we can also say is that the average gradient between those 2 points is 2, because that's how you calculate average gradient. You take y2 minus y1 over x2 minus x1 for any curve, not just a straight line, and you work out what the m is. That's average gradient. But this question was asking us also, what is the gradient at any x value on the straight line? Well, it's going to have the same gradient throughout. It's going to have a constant gradient. Therefore, the gradient will always be 2. Okay, if you're interested in finding out the equation of the straight line, it's 2x minus 7. Y is equal to 2x minus 7. There's the gradient in front of the x. Okay, that's the m in y is equal to mx plus c. All right, so that's just a brief reminder of how to calculate gradient and average gradient. Okay, now let's go for the problem. So the problem is this. How do we calculate the gradient at a single x value for any curve? Okay, so when I mean curve in this sense, I'm not just talking about straight lines this time. I'm talking about curves that look like this, curvy curves, right? How do I calculate the gradient at this point, or the gradient at that point, or the gradient at that point? What are the gradients at these points here? Because it's no longer a straight line. If I use m is equal to y2 minus y1, okay, y2 minus y1 over x2 minus x1, where these values, okay, these values are points on these curves. They are basically two coordinates on these curves. I'm just going to get average gradient. And I don't want the average gradient between 2 points. I want the gradient at a single point, at that specific point and that specific point only. So that's the problem. How do we calculate what that is? Okay, so let's try and visualize what this specific gradient at a point would look like. So what we're going to do is I want you to consider the function y is equal to x squared. Okay, that's your standard parabola. Okay, how do we visualize and calculate the gradient of a curve? Notice that this is a curve, it's a curvy curve. Okay, there's the parabola in red. How do we calculate the gradient of a curve at a specific x value. So at a single x value, or you could say at a single coordinate if you want to. Okay, we use a tangent line. So a tangent line can be interpreted as a straight line that touches a curve or graph once at a single point. So if I have a curvy curve, let's say it looks, let's try and draw it better, like that. Let's say I wanted the tangent line at that point. So the tangent line is a straight line and it will touch, let's try and draw it a bit better. It will touch it once at that point of tangency. It's called a point of tangency or point of contact. It will touch it once here. Okay, and that's what a tangent line can be thought of or interpreted as. That's what it actually is in layman's terms. Now, what's so special about this tangent line? Why am I telling you about this? It turns out that the gradient of the tangent line will be equal to the gradient of the curve or the function. Okay, this is the same thing at the point we are considering, and that point we are considering is called, just for your information, it's called a point of tangency. Okay, so for example, I want you to consider the tangent line of y is equal to x squared, so the parabola at x is equal to 1. So in red, I have the parabola y is equal to x squared. We go to x is equal to 1. There's that point there. Just let's make sure that's the correct point. X is equal to 1. We expect the y value to also be 1 because you sub in 1 in x squared, you'll get a y coordinate of 1. So we are at the correct point. Now, the blue line that I've drawn here, that line there, that is called the tangent line. Notice how it is touching the y is equal to x squared graph, the parabola, at the point 1 and 1, the point of tangency. And I want you to see, notice how the gradient of this blue line is exactly the gradient of the parabola at the point of tangency at that 1 and 1. So look at how these two are basically overlapping at that point. The gradient is the same at this point 1 and 1. That is why we say that the gradient of this tangent line is equal to the gradient of the parabola at that specific x value, x is equal to 1, or the coordinate 1 and 1. If I wanted to find the gradient at this point, okay, let's say that looks like minus 1.4 or 1.5 something. Okay, if I wanted to find out what's the gradient at this point here, all I would do is I draw a tangent line. Let's see if I can draw it a bit better. Draw a tangent line to the parabola, that's the best I can do, and find out what's the gradient of that tangent line. And that will give me the gradient of the parabola at that specific point that I was considering. So that's why tangent lines are so important to visualize gradient at a point. Okay, and I want you to notice here, we are considering gradient at a single point. We are no longer taking 2 points on the curve, okay, and calculating the average gradient between these 2 points. That is where you would take y2 minus y1 or over x2 minus x1. This right here, okay, if I had to draw that, let's get this out of the way. This right here is average gradient. It's going to give you an approximation of the gradient at a point, but it's still an approximation. Okay, you can get it quite close with an approximation, but it's not the exact answer that we want. This is average gradient when you take y2 minus y1 over x2 minus x1. Okay, we are considering gradient at a single point. It's sometimes called the instantaneous change at that single point. Just a note in case you're wondering, y2 minus y1, the average gradient formula, it will always work for a straight line because average gradient formula gives us a gradient that is based on a straight line. And if we are working with a straight line, the approximation is going to be the exact answer. Plus the straight line has the same gradient throughout, no matter which 2 points you consider. So that's just for example 1 that we did previously. Okay, so that's the problem that we want. Okay, finding exact gradient at a single point. How do we do that? And this is where the derivative comes into play. So coming from the previous slide, it means that if we could calculate the gradient of a tangent line to a function at a specific point or x value, what we calculate, okay, the gradient of that tangent line, what we calculate for that gradient of the tangent line is actually the gradient of the function at the specific x value that we are considering. Okay, that's nothing new. It's just what I've explained on the previous on the previous slide. So let's get into the derivative and what it means. I want you to consider the function f of x, okay? This is a function that I give you. Let's call this the original function. So f of x, that's the original function. The function f, and it's got a little comma there, x. This here is read as f prime x. This little, not comma, it's an apostrophe. That apostrophe after the f is read as prime. So the function f prime x is called the derivative of the original function f of x. So I'll give you f of x. Okay, I'll give you the original function. And then what you are going to do is find f prime of x. F prime of x, this one here, this f prime of x is the derivative of the original function. Why is it so special? Why is it called derivative? Why am I telling you all of this? F prime of x returns the gradient of the original function, which is f of x, at any x value that you want to examine. So let's say I give you the function f of x, and then you use some mathematical magic and you find out what f prime of x is. This is the derivative, okay, more specifically the first derivative, but don't worry about that now. It's the derivative function now. Why is this so special? Well, let's say you wanted to find out what's the gradient of the original function when x is equal to 2 or at the coordinate 2 and whatever the y value is. What's the instantaneous rate of change, or what's the gradient of this f of x function at x is equal to 2? All you have to do is, well, you found your your derivative function, then you just substitute 2 into your derivative function, and let's say you calculate an answer of 4. Okay, let's say you calculate an answer of 4. What this means is that the gradient of the original function when x is equal to 2 is equal to 4. So it's going to have kind of a slope of 4. Okay, so the function will be looking quite steep at x is equal to 2 because it's having a gradient of 4. Let's say you then wanted to find out what's the gradient of the original function at x is equal to minus 3. All you have to do is substitute in minus 3 into your derivative function. Let's say it gives you an answer of 7. That means at x is equal to minus 3, the original function will have a gradient of 7. Okay, or you can say it has a derivative of 7. When you hear the word derivative, I want you to think about gradient. Okay, technically it has a derivative of 7, but for explanation purposes, I want you to think about gradient because that's what it is at its core. Okay, so that's what the derivative function does. So when you insert a value into it, it is going to give you a gradient as its output. And the gradient is going to be the gradient of the original function. Okay, and I'll show you how to derive these first derivative functions. Okay, so this is the formula that I want you to take note of. Okay, f prime of x, or the first derivative, is equal to the limit as h approaches 0 of f of x plus h. So if I give you a function f of x, right, let's say f of x is equal to x squared minus 2, what you're going to do is wherever you see x, you're going to substitute x plus h, right? And that will give you f of x plus h. Then you're going to subtract f of x, and then you're going to divide that all by h, and then you'll take the limit as h approaches 0. Okay, so this is the formula that I want you to know when you're working with first derivatives of a function and finding out derivatives. There are other ways that this formula is presented. Some have f of x and f of a and derivative at a specific point that you're considering. I just want you to learn this one, okay? Because then you can get your derivative function, and then you can learn, then you can work out the derivative at any point if you have this function. Okay, let's get rid of all of that. So just a note, when you find the derivative function, the f prime of x, using this formula here, you are finding the derivative using first principles, okay? So when you use this formula, it's called finding the derivative using first principles. So why I'm telling you this is because sometimes in a test or exam or question, they might ask you to find the derivative using first principles. You'll go to this formula. Just basically means use this formula. Why? Because there are other ways of finding the derivative, much easier, much faster ways that we'll cover later. But right now, I'm going to show you how to find derivatives using first principles. Okay, so that's a lot of notes, a lot of talking. Let's go for an example and see how this all works out. Okay, so take a look at example 1. All I want you to do is apply the formula. So find the derivative of the function f of x is equal to x squared using first principles, basically using the formula that I showed you on the previous slide. So pause the video and complete this example. Okay, let's go for this example. So let's write out the formula for the first derivative. Okay, f prime x is equal to limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, that's the formula. The first thing that I want to do, or basically the hard work that I have to do, is, for this example, get f of x plus h. And I'll help you through this on the first example, and then you should be able to handle it in the other ones. So f of x is equal to x squared. To get f of x plus h, I'm simply going to write down everything I see in f of x, except wherever I have an x, I'm going to replace that x with brackets. So in the f of x function, I have x squared. So in place of the x, I'll write down the brackets, and then I'll square it. Okay. Then last step, in place of the brackets, write down what you're substituting in. So it's going to be x plus h. And that's how you make your substitution. This is how these are the steps that you can use to make any substitution. Replace x with brackets, and then fill in what you have in your substitution function, what you're substituting. So just for example, if you had minus x, obviously you'd fill in minus x there. Just a slight deviation in case you needed help with substitution. But anyway, back to derivatives. Okay, so what we're going to do now is we're going to expand this. If you expand this and you use FOIL, or maybe you can just expand it by looking at it, it's going to be x squared plus 2xh plus h squared. Okay, that's f of x plus h. So this is what we're going to do. We have f of x plus h. Let's just take this out and keep it on top. Okay, we'll use it right now. So f prime of x is equal to the limit as h approaches 0 of f of x plus h. So it is this portion here. We're going to take that there, minus. And what I encourage you to do when you're doing this minus is you have the minus there. So that's why we have minus f of x. Do not just write out f of x as is. Always write down your brackets and then put f of x inside. Okay, because sometimes, and this may happen to you, you may have a negative sign in front of your function, and you may forget the negative sign, and then things are going to go haywire. So always write down your brackets and then put f of x inside it, just so you don't make a problem with the negative and positive signs. Okay, so it's f of x plus h minus f of x, right? Remembering to put that f of x in brackets so you don't have a problem, all over h. Now, what we need to do now is check if we can solve the limit, because this is a limit problem after all. Well, we have limit as h approaches 0. How do we solve limits? Let's check if I can substitute h is equal to 0 into this function here. And surprise, surprise, I can't. Okay, that's part of how you work out derivatives. Okay, I can't substitute it in immediately. I'll get division by 0, and that's undefined. What I need to do is simplify this numerator such that I can pull out a common factor of h. If I can pull out a common factor of h, it will cancel off with this h at the bottom, and then I can hopefully substitute in h into the function that remains. So let's work with the numerator. Let's leave the denominator for now. We have x squared minus x squared. That is going to disappear. So on the top, I'll be left with 2xh plus h squared. And this is great because now I can pull out a common factor of h. If I do that, I'll end up with h into 2x plus h. And then these two can cancel off. So it's going to be limit as h approaches 0 of 2x plus h. Ask yourself, can you just substitute in h is equal to 0 right now? Yes, you can. And I won't have a problem. So I'm going to do that. Once I do that mental substitution, I'm going to have 2x. So there it is. There's the derivative function, f prime of x is equal to 2x. But what is the significance of this? Why have I done all this work? Okay, here's my original function. Remember from the previous slides, I was interested in finding out what's the gradient or instantaneous rate of change of this function when x is equal to 1. And I didn't want to use the average gradient formula, y2 minus y1 of x2 minus x1. Well, now I can find out what that is. I take in the x value that I'm concerned with, and I substitute it into my first derivative function, and I'm going to get 2 times, substitute 1 in place of x, and I'll get 2 times 1, which is 2. So let's just go back to the picture that I had. It means that the gradient of the parabola at x is equal to 1 is 2. And it looks reasonable. A gradient of 1 would look like this, and this one is steeper than a gradient of 1. So it looks like it's going to be 2, but it is in fact actually 2. What you can also do, and what I encourage you to do, is take other x values. For example, x is equal to minus 3, x is equal to minus 4, 0, whatever the case may be, sub it in this function, right? Find out what the gradients are, and check on a picture, okay, on a drawing of that parabola, if those seem reasonable, okay? Check that the negative x coordinates or the negative x values do in fact give you negative gradients, because if you look at the parabola, it looks like that. Negative slopes all around on for your negative x values. So it should have negative gradients. Once you're dealing with positive x values, you should have positive gradients. And the higher or the further out you go for your x values, right, the larger the magnitude of that gradient. Okay, so you should be getting, like, let's say using 10, you should be getting like 200. If you're using minus 10, you should be getting negative 200 as your gradient. Sorry, not 200, negative 20 and negative 20 and positive 20. Okay, not 100. Okay, so try and do that and see if it makes sense, right? That's the gradient function. That's what it does.